Let's consider the function f of x equals the absolute value of 1, fourth times the quantity x cubed minus 3x plus 2. We define a new function, g of k, as the maximum value of f of x over the interval from k minus 1 to k plus 1. So for each real number, k, g of k gives us the highest value that f of x reaches between k minus 1 and k plus 1. Now, we are told that g of k is discontinuous at certain values of k. Let's say all of those discontinuities occur inside an open interval from a to b, where a and b are integers. Our goal is to find the smallest possible integer, a, and the largest possible integer, b, such that all discontinuities of g of k lie strictly between a and b. To begin, let's take a closer look at the expression inside the absolute value. We define a function g of x as 1/4 times the quantity x cubed minus 3x plus 2. To find the critical points of g of x, we take the derivative. G prime of x is 1/4 times the quantity 3x squared minus 3. Factoring, this gives us 3/4 times the quantity x squared minus 1, which equals 0 when x is -1 or +1. We evaluate g of x at these points. At x equals -1, we get 1/4 times -1 plus 3 plus 2, which is 1, so that's a local maximum. At x equals 1, we get 1/4 times 1 minus 3 plus 2, which is 0. That's a local minimum. Now, let's consider some other helpful points. At x equals 0, g of x is 1/4 times 2, or 1/2. At x equals -2, g of x is 0. And at x equals -3, g of x is -4. Next, we apply the absolute value to g of x. This reflects any negative parts of the graph above the x-axis. So, for example, the point -3, -4 becomes -3, 4. The new function f of x is always non-negative and follows the shape of a smooth, piecewise curve. Now, let's analyze how g of k behaves. Remember, g of k gives us the maximum value of f of x over the interval from k minus 1 to k plus 1. As k increases or decreases, this interval slides along the x-axis. We want to know where the maximum value inside that interval changes suddenly, that is, where g of k becomes discontinuous. Let's think of the interval moving toward the point, x equals -3. As k decreases, the interval slides to the left, and the left endpoint, k minus 1, gets closer to -3. During this process, the maximum value of f of x inside the interval gradually decreases, following the shape of the curve. Eventually, when k minus 1 is between -3 and -2, it reaches a point where f of k minus 1 equals 1, the same value as the previous local maximum at x equals -1. Then, suddenly, the point x equals -3, where f of x equals 4, enters the interval. At that moment, the maximum value jumps from 1 to 4, and that jump causes g of k to become discontinuous. This first discontinuity occurs when k is between -2 and -1. Next, we look for a second discontinuity, one that occurs when the maximum value switches abruptly from one endpoint of the interval to the other. This happens when f of k minus 1 equals f of k plus 1. We solve the equation. G of k minus 1 equals g of k plus 1 using the original cubic function. After expanding and simplifying, we find that this occurs when kg equals plus or minus the square root of 6 divided by 3. Among these, only the positive value, approximately 0.816, causes a discontinuity because it's in the region where the maximum changes sharply. Now we've identified two discontinuities. The first occurs when k is between -2 and -1. And the second occurs when kg equals the square root of 6 divided by 3. To answer the question, we need to find the smallest integer a and the largest integer b, such that all discontinuities lie within the open interval from a to b. The first discontinuity is greater than -2, and the second is less than 1. So, the smallest such integer a is -2, and the largest such integer b is 1. Final answer: a equals -2, and b equals 1.